5, and 6, or 1, 2, 3, 4, 5, and 6. You could do it either way. So if you do the purple lettering, which side of the ring is your diene? Right side is your diene. The left side is your dienophile. So your dienophile would be 2 carbons with a pair of hydrogens on it. Okay. If you use the red lettering, what is the left side of the ring going to be with the red lettering? The diene, and the right side is our dienophile. What do we know about dienophiles? What are the best dienophiles from the mini lecture? Ideally, dienophiles have electron withdrawing groups on it. Acetylene would not be a very good dienophile. I take it on a problem like this as a correct answer, but this is not electron poor. So it would be better to have the red numbering here, because the electron withdrawing group right here would be on our dienophile. All right, so let's go backwards. On a problem like this, we can draw our generic diene, can't we? And we can number it 1 through 4. What kind of a dienophile are we going to have? An alkyne. So we number it 5 and 6. And now we can just map shrubbery. Whatever the substituents are in the product were present in the starting material. So help me out. What do we need to put on carbon number 6? Ketone. So we put on a carbonyl group and a methyl. How about carbon 5? Hydrogen. Okay, how about the diene? Carbon 1. Ethyl group, and where do you want to put it? Inward, okay. Hydrogen is up here. How about on carbon number 4? Another ethyl, and where is it going to be? Out. So can you see that whatever the 2 groups are that are in end up cis to one another. Whatever the 2 groups are that are out end up cis to one another. Yeah, Anthony.
Just in the product, you have the, on top you have the hash at the H, and then at the bottom you have the dashes at the H. As can see.
Oh, this is a hash on hydrogen. That's a wedge on hydrogen.
Thank you.
Mm-hmm. So these 2 groups are trans to one another here. So they end up having to be in different positions here. 1 in and 1 out. Okay, how do you feel about Diels-Alder after that? Is that okay? There's only one other kind of Diels-Alder that we might want to practice, and that's one where the diene is in a ring. One year, I always drew the diene on the left and the dienophile on the right. When it came to the exam, people always assumed that the left molecule was always the diene. So I had to get more sneaky after that and teach it where they kept switching places so people didn't just immediately assume the left molecule is the diene. So that's one of your first tricks, is you got to be able to figure out who's the diene and who's the dienophile. By definition, the diene is a molecule with two carbon-carbon double bonds attached to one another, not one carbon-oxygen double bond and a carbon-carbon double bond. So who's the diene here? It is on the left this time, yes. Just messing with you.
I know, like, what? I thought you were saying that it was on the left. I was like, wait, what?
See, I like making you question things, make you think about what you're doing. Yeah. Messing with you is the correct statement. Okay, what part of the right molecule is the dienophile then? Good. So you might grab yourself some colored pencils, circle the parts of the molecule that are going to react, just to help guide you towards what is going to happen in the reaction. Okay, we're going to form a 6-membered ring. We can go ahead and draw it. 1, 2, 3, 4, 5, and 6. Help me out. Double bond between 2 and 3.
Would the oxygen between 1 and 4 be on a hash or wedge? Is that like it?
The answer is yes.
Oh, it's on both. Okay.
And put it on a wedge for right now.
All right.
We draw it in the middle here.
If that's on a wedge, does the CH3 have to be on a hash?
No, because we would never have a carbon that looks like this. You get a nasty comment on your exam saying roadkill carbon. Because whenever we do hash wedge notation, the hash and the wedge must be right next door to one another. So if you're going to do that, you need to make this group a hash, because they're right next to one another. Or that group a hash. You couldn't make the one opposite hash. But we're going to kind of assume that since we put one wedge on here, we can kind of get the sense that this is poking us in the face. This one's to the left, this one's to the right, and then this one is straight down.
Does it matter if we put the methyl on the 1 or the 4?
It does not, because we could have numbered it 1, 2, 3, 4, or 1, 2, 3, 4. Either way.
Do we need to show both, or just one is fine?
Let's figure out what their differences would be when we actually finish the structure of the product. Figure out what the relationship might have been. Okay. Okay, what else do we need to do? Okay, and where are they going to be?
1, 5, and 6.
And what relationship are they going to have in the product?
Cis.
They're going to be cis. So the two groups here are cis. The two groups here are going to be cis. And then David's going to ask, are they up or are they down? And I say, yes. You get both, right? Either both groups are up or both groups are down. What's the relationship between those two molecules? Diastereomers, so you draw them. Okay, so that's a full point answer there. So Cynthia, you asked if we numbered it the opposite direction.
It would be the same.
We get the mirror image of this molecule. And if we did the opposite numbering here, we'd get the mirror image molecule. You don't need to draw mirror image molecules, but if diastereomers form, you should draw them. The oxygen could have been on a hash. And if you did that, if this oxygen was moved to a hash, you'd have the mirror image of this molecule. If you drew the oxygen on a hash here, you'd have the mirror image of this molecule. So all we have to do is to draw it on a wedge and change the other half and know we're going to get enantiomers, but who cares about enantiomers? It's diastereomers that we care about. Okay, Diels-Alder pretty well dead now? You feel pretty good about that?